So, I have told you how to generate test vectors for digital circuits, but I have only looked at combinational circuits. Okay. So, as you may remember, in a combinational circuit, there are some primary inputs and primary outputs, and the outputs are decided as soon as the primary inputs become available. Okay. Testing combinational circuits, I have told you, is a challenge by itself. Okay. There is no efficient algorithm, frankly speaking, right. So, there are no polynomial time algorithms. I think I have mentioned this before. So, backtracking algorithms are used. So, examples are D and PODEM. Okay. And in the worst case, they may sort of do a lot of backtracking and take exponential time. So, there are some what I would call as pathological cases. So, there are pathological cases where these algorithms take too long to find a test, because they are looking at every possible input. So, because of this, we can put a bound on how many times you can backtrack. Okay, we can say no more than 100 backtracks. So, this will limit the total amount of run time that you will spend on these algorithms. So, this is what tools do, right. Remember, I mentioned to you tools like Synopsys ATPG tool and Cadence ATPG tool, Siemens ATPG tool. Okay. They all try to put a bound on the number of backtracks. So, as a result, sometimes there may be an opportunity, or there may be a situation where some tests are considered aborted, meaning it says no, I couldn't find, okay, within the time you allotted, I could not find a test vector. So, it may abort the faults, some faults. Okay. So, when that happens, the engineer will possibly increase this. So, let us try 150 and see whether it works, or 200. So, it may take longer, but it may succeed this time. You may have also wondered, right, so let me assume that there is a combinational circuit. Let us say these are some primary inputs and some primary outputs. I did mention to you about random testing, right. I told you that I can try to apply some random vectors, okay, and do a fault simulation and find all the tests that the random vectors are catching, and that I have mentioned to you that as you increase the number of random vectors, initially you will get a good number of faults getting detected. Okay. So, this is the number of faults getting detected. This may be the total number of faults. So, they will find if you are willing to spend a lot of random tests, you may be able to get maybe 40-50% of those. Okay. So, these are not detected. So, I may actually have quite a few other faults which are not detected. So, beyond some point random testing may not help. Okay. So, this is the number of vectors. So, the faults which do not get caught by random tests are we call them as random pattern resistant. So, they resist being caught by random patterns. So, we have to use algorithms like D algorithm or PODEM, right, which are expensive. Random patterns are easy to generate, right, it is very easy to generate random numbers. Now, why do they resist the why do some faults resist being caught by random patterns? Okay. So, here is where there is a concept of controllability and observability. So, you see in a combination circuit the primary inputs are fully controllable. So, these can be controlled to any value. So, controllability is 1, controllability is high, very high controllability. As you move through the gates, okay, if I give you an internal point and say control it to some value, its controllability will be low, because I had to somehow set these primary inputs in order to get that value. On the other hand, the outputs are fully observable, full observability, you can see what they have. But if I find some point inside and then say, hey, what is the value on this, is it 0 or 1, I can't observe it directly. Okay. So, internal lines are difficult to control and observe. Okay. The further you get away from the primary inputs, the lower your controllability, and similarly the further you get away from the primary outputs, the lower your observability. Okay. See, let me give you an example. So, if I have something like this, see this line I can control it to anything I want, this is a primary input. But if you want me to control this line to a logic 1 or something like that, I had to first control the OR gate here. Okay. So, maybe I can do it by setting this to 1 and this to 0 or x, and this one can be controlled indirectly by putting this and so controlling an internal line gets harder and harder as we move away from the primary inputs. Similarly, if I want to see what is there on this line, I can directly observe this line. I can connect this to an oscilloscope, or I can connect it to a multimeter and I can see what the value is. But if I want to know what is the value here, I will have to propagate this line. So, I can control this to a 0, so that this value comes here. I can control this to a 1, so that it moves here. I can control these two to 0, so that it becomes available here. Now, I can see what is there on this line. Okay. If this line had the value x, x plus 0 is x only, x dot 1 is x only, and x plus 0 is x only. So, I can observe this line indirectly at the primary outputs. So, this is what one means by controllability and observability. Okay. Sometimes people put some numbers to measure. So, let us take this circuit. Let us call this as A, B, C, D. We say that combinational controllability of A to 0. Okay. That means, let me just rewrite this. CC0A means controllability, combinational controllability of A to value 0. Similarly, I can say CC0 of B, CC0 of C, and CC0 of D. These are very controllable, so we can put a low number like 1. So, 1 means the controllability is very high. Now, let us look at this AND gate. If I have to control this to 0, then I can either control A to 0 or this wire to 0. Okay. Let us look at this wire here. Let us call that as E. What is the combinational controllability of E to 0? How do I control E to 0? I will either set B to 0 or C to 0, and I will choose the easiest of the two. So, I will say minimum of combinational controllability of 0 of A and combinational controllability of 0 to, I am sorry, this is not B. So, I will choose the minimum value of the two, because I will try the easiest way to set E to 0. In addition to that, I will put a plus 1, so that I can say that it is further away from the primary inputs by one gate. Okay. So, in this example, it will come out to be minimum of 1 comma 1 plus 1, so it will become 2. So, this is CC0 of 2. If this is called F and G, CC0 of F, once again I will choose the minimum effort, because it is an AND gate to set f to 0, I can set either a to 0 or e to 0. So, I can say it is the minimum value of C C 0 of a or C C 0 of e plus 1. In this case, this comes out to be 1 comma 2. So, minimum of 1 comma 2 is 1. So, this is also 2. This is an AND gate, and if I have to send the output of the NAND gate to 0, I have to make f equal to 1 and g equal to 1. So, this is a little harder. So, C C 0 of g, I have to make both f and g equal to 1. So, I have to say it is C C 1 of f plus C C 1 of g plus 1. Earlier I was using a minimum function, but now I will use a addition. To say that it is harder, I have to achieve both, and moreover I have to use C C 1 now, because I have to set both f and g to 1 in order to get 0 at the output of this h. Oh, I am sorry, this is what I meant, this h is what I meant. We have not yet figured out how to calculate C C 1 of f, etc. So, let us do that. So, C C 1 of f, it is an AND gate. So, to set the AND gate output to 1, I had to add the C C 1 of a plus C C 1 of e plus 1. Now, C C 1 of a is 1 because it is a primary input, whereas C C 1 of e, it is an AND gate. So, to set the NAND gate output to 1, any one of them can be used, either B can be set to 0 or C can be set to 0. So, again I will say min of C C 0 of B or C C 0 of C plus 1. So, in this example it is minimum of 1 and 1. So, the answer is 2. So, here it will become 1 plus 2 plus 1 or 4. So, C C 1 of f is 4, C C 1 of g, C C 1 of g is what? It is an OR gate. So, either I can set e to 1 or d to 1. So, you have to say min of C C 1 of e or C C 1 of d plus 1. Now, what is C C 1 of e? It is an AND gate. So, either I have to set B to 0 or C to 0. So, C C 1 of e is nothing but min of C C 0 of B or C C 0 of C plus 1. So, this becomes 2 and D is 1, okay, because it is one of the primary inputs. So, minimum 1 and 2 is 1, 1 plus 1 is 2. So, G C C 1 of G is 2. So, if you plug that in here, you will get the answer as C C 1 of f is 4 plus C C 1 of G is 2 plus 1. So, it is 7. So, this is what I meant by saying as you move away, controllability becomes higher and that means more difficult. Okay. So, controllability gets higher and higher. Okay. So, I hope everybody understood the idea of combination of controllability to 0 or 1. We can do the same thing for observability. we can say that combinational observability of H is 1. Because it is the primary output. What about the combinational observability of F? To observe F, we must control G to 1, right, and then we have to observe H. Okay. So, we can say we had to do C 1 of G plus C O of H plus 1. That 1 is added just to say that we have gone a little deeper. Okay. Now, CC1 of G I think we calculated earlier as 2. So, this is the observability of F. In the same way we can find the observability of G. Combinational observability of G. In order to observe G, I have to set F to 1, only then I can observe G. If I set F to 0, then I can't observe G. So, I have to set F to 1 and then observe H. So, this is also I think 4, right. No, yeah, this is 4 plus 1 plus 6, actually this is 6. So, this is how you can sort of calculate the observability. As you can see, if I go inside, the observability numbers go high, okay. They become large. If you have large numbers on observability, that means that node is very difficult to control or observe. You understand? So, if I have a big combinational circuit with millions of gates, as I calculate the combinational controllability, observability, etc.,